Hello.
Good evening, sir.
Yeah. Good evening. Can you hear me?
Yes, sir.
Board exams are over.
Yes, sir.
Okay. Or one is left or everything is over.
No, mine is over. I
Okay.
am from state board. That's why.
Okay. So now your JE preparation is going to start, right?
Yeah.
Okay. Fine. We'll just wait for other people also to join.
Hmm.
Just hold on for a minute or so.
Good evening, sir.
Yeah. Good evening. So earlier we had been doing geometry where we had done angle chasing and there were a lot of problems that we had done. You have to try to attempt till the end of the last sheet. So I think there are around 275 problems there, right? Till problem 275 we had reached.
Yes, sir.
Yes.
We might have discussed, I think 210, 220 around that we have
Yes,
discussed.
sir. Yes, sir.
So the remaining problems you have to attempt over the next 2, 3 weeks and at least the next couple of weeks and try to finish them and we'll discuss them. However, we will continue with the next part of the geometry course where we have to do some theory which is slightly advanced. So this part of the course will cover important configurations that you should be familiar with. Uh, Important configurations, some theorems that you need to know. We'll do some practice problems, but less problems and more theory, and theory guided by some questions. And then we have to do some advanced techniques, which will be complex numbers and vectors, complex numbers and vectors in geometry. So at least these two things we need to cover properly. And that is the idea. So we'll start off with these things now. So what you should be doing is when you make notes, make sure that you write down all the theory that we are doing and revise the theory. It will be useful for you in the future as well. So make good notes for this part of the thing. All the basic theory we already know, whatever we have done so far, all the basic stuff is already covered. So now it will be slightly more advanced. We will do the
Yes, sir.
class for the doubts of those questions that were assigned earlier, probably next week or sometime. Right now, we'll start with the theory that we are going to cover. So, the first thing that I want to talk about today is power of a point, and we'll start with that. And that is a pretty basic thing that all of you are already familiar with. So, I'll just write the definition. Let tau be a circle and P is a point. Let the line through P meet the circle, meet tau at points A and B, and let another line through P meet the circle at points C and D. Then we can show that PA times PB is equal to PC times PD. Also, you can also prove that PA times PB is equal to PT square, where T is the point of tangency from P to the circle. So basically this theorem everybody knows, right?
Yes, sir.
So power of a point PA times PP is equal to PC times PD. Basically, if you know a point and are given a circle, then always the product of PA and PB is equal to PC and PD and is also equal to PT square if this is the tangent. Because the same line can be turned a little bit like this. And as you come closer and closer to the tangent, the points C and D become closer and closer to T, right? So PC and PD will both become close to PT and PT once you become tangent, right?
Yes.
Also, by Pythagoras theorem, we know that PT square is equal to OP square minus R square, where O is the center of the circle and this is the radius, right? So we can say that power of point P is equal to OP square minus R square modulus. The reason I have put a modulus is because power of a point is positive when the point is outside, but power of a point is still possible to define even if the point is inside the circle. In that case, it will be R square minus OP square. Is everyone understanding what I'm saying?
Yes, sir.
So the proof of this is easy and you can do it by similar triangles. PA times PB is equal to PC times PD. I will not do the proof. That is obvious. You should be able to do it yourself also. Try to connect AC and BD and see which triangles are similar and what is happening. You should be able to prove this. Is it okay? Can everyone try that?
Yes.
Yes.
So do that after the class. We will go on to some applications. So the second thing that I want to talk about today is Euler's theorem. So all of the topics that we are going to discuss from now on in geometry are going to build up on top of one another. So when we are discussing the point number 2, that is Euler's theorem, we are going to use power of a point and we are going to slowly construct our geometry knowledge one on top of the other. So make your notes like that so that you know exactly what has been discussed and what is required for the next thing. I hope you understand what I mean.
Yes. Yes.
So we are going to understand things in relation to one another. So make your notes nicely so that you can revise everything easily. So Euler's theorem says that if there is a triangle ABC where O is circumcenter, I is in center, R and small r have usual meanings, circumradius and in radius. You have to prove that OI square is equal to R square minus 2R capital R. This is what you have to prove. Basically, you have to find the distance between circumcenter and incenter. There are two ways to do it. I want you guys to try to prove it right now. One way is by trigonometry, and that method has been shown in SL if anybody has read it. SL chapter 15 has the proof.
Yeah. Yes, sir.
You should know how to do that. If you can't do that, then there is the geometry proof that we will be discussing. And the geometry proof will involve power of a point. So you have 5 minutes, 5 to 7 minutes. You have to try to figure out this proof. Just try it out right now. I'll be back in 3-4 minutes. Okay, try out the proof. Are you getting something?
No, sir.
You have not done SL only? Does anybody know the SL only proof? Trigonometry proof.
Yeah. Yes, sir. But I'm finding the geometry proof.
What is the trigonometry proof? How can we do the trigonometry version?
I don't actually remember exactly the proof, like step by step.
कोई
I'll-
प्रोग्रेस कोई भी प्रोग्रेस नहीं होगा अगर तुम लोग वो नहीं करोगे जो मैं करने बोल रहा हूँ तुम लोग को. There is no chance of any progress. If you don't do SL only, if you don't do what has been recommended, then what will be the benefit? Why has nobody done chapter 15? Nobody knows chapter 15, the proofs that are there in that. I have been saying this since the classes started that you have to do that chapter. Nobody has bothered. Aniket, why have you not done chapter 15?
I have done chapter 15. Not the questions, but the theorems.
This is one of the theorems.
Yes, so let me just check, sir.
You don't need to check. This is article 238 or something. OI square, OH square, OI square, all of it has been derived. If you don't do your work that is being asked, there is no chance of any real progress. So first we'll discuss the SL proof. You need to know OI distance. I is my incenter, O is my circumcenter. If I want to find this distance, I need this distance to be part of some triangle. What I mean by that is I cannot just keep a hanging OI in space and hope that I'll find that length. I need to make it part of some triangle. I will
Yes,
join
sir.
A to O. If I join A to O, at least I have a triangle AIO.
Yes.
In this triangle, I know length AI is R by sine A by 2. I know length AO is equal to capital R. I need to find OI distance. All I need is this central angle. That angle is very easy to find because I know these angles. This angle will be 2B, so this much is B. This is 90, so this is 90 minus B. So this is also 90 minus B. And B by 2 is this, A by 2 is this much. So A by 2 minus 90 minus B is my required angle. It is A by 2 plus B minus 90, which is A by 2, B by 2, C by 2. So we are getting this required angle is B minus C by 2. In triangle AIO, I need this distance. I know this, I know this, I know this angle. It is obvious cosine rule with angle B
Cosine.
minus C by 2. Anybody who has read the book will be able to say this. This is not some magical method. It's an obvious thing. If you do cos of b minus c by 2 is equal to ai square plus ao square minus oi square by 2 ai times ao, you will be able to solve for oi square. After a lot of simplification, you can prove that oi square is equal to root of oi square is equal to r square minus 2r small r. In SL the formulas are given in terms of r root over 1 minus 8 sin a sin b sin c, something like that. If you see the SL book, this is the formula that you will find. Is it there? Have you seen?
Yes, sir, it is there.
They are for half angles.
I don't remember exactly whether it is half angle or full angle. I think it will be half angles. But it will look like this, which is actually same as this. Because
Yes,
we
sir.
know that small r is 4 capital R sin a by 2, sin b by 2, sin c by 2. So if you simplify everything from here, it will be a long simplification, but eventually you can get here. This is very straightforward and it is expected from all of you to know this. We are going to talk about the geometry proof now. This is my in center. These are angle bisectors. I'm going to extend the AI line and I'm going to meet the circumcircle at a point D. So basically the angle bisector of A has been extended so that it meets the circle at point D. Our job is to find OI square. I have not marked O here because the picture will become complicated. O is the center of circumcircle. We are not going to mark O in this figure. The point here is this thing. If I think of power of a point I, power of point I with respect to circumcircle, that will be equal to IO square. Actually, that will be equal to R square minus OI square. Why? Because the I point is inside the triangle or inside the circle. Since the incenter is inside the circle, power of a point will be written as R square minus OI square. Is everyone understanding what I'm saying?
No, sir.
Yes.
What do you mean, no, sir? What is power of a
Okay.
point for points inside the circle?
R square minus OP square if we are taking point P.
So what is the point I here?
Okay, yeah, got it, sir.
This is my power of a point, and obviously I can say that from this figure, power of a point I with respect to this circle is IA times ID. IA times ID will be equal to this, right?
Yes.
So OI square is equal to R square minus IA times ID. We are getting this. So now our job is to prove this formula. So our job is to prove that IA times ID is equal to 2R small r. If we can prove that, then it is over. Here we already know the value of IA. It is R by sine A by 2.
Sine by 2.
So all we have to find is the value of ID and prove this result. So now we will join B and D. I need to find ID. If you think of angle BID, angle BID is equal to angle BAD plus ABI. Because
Yes,
it is
sir.
the exterior angle
Exterior angle.
of this triangle. Angle ABI, we will, okay, first we will say BAD is going to be the same as CAD. One second. BAD and CAD are same? Yes, because this is bisector. Why is BAD and CAD going to be same? These
So because
angles
I
are
is
equal.
yes, sir. I is angle bisector.
So this is bisector, that's why CAD plus angle ABI, and CAD is going to be same as CBD plus angle ABI. And angle ABI now I can write as ABI, can be written as same as CBI. Why? Because this is also angle bisector. ABI is same as CBI. And now I'm getting CBD plus CBI, which is clearly angle DBI. Can you see what I'm saying?
Yes, sir.
We are getting angle BID is equal to angle IBD. So that makes the triangle BID isosceles. And that means that ID is equal to BD.
R upon sine.
No, it is not R upon sine B by 2. Which angles are equal?
Angle DBI and angle
Oh, okay,
BID.
okay.
We have BID and this angle. So ID is equal to BD. And if we know ID is equal to BD, then we can now think of triangle ABD. In triangle ABD, if we do sine rule, we can say triangle ABD sine rule BD by sine A by 2 is equal to 2 capital R, because this triangle has the same circle as the original triangle. Do you understand what I'm writing here?
Hmm.
So from here, BD is coming as 2 capital R sine A by 2.
Sir, how will it have the same size?
Triangle AB, what was point D? How did we find point D? It was not mentioned in the question. What did we do to get D?
We extended it.
So obviously it meets the same circle, right?
Okay.
Triangle ABD has the same circle as ABC.
Okay.
Is it obvious?
So aren't we supposed to like take another center if we have to find the circumcenter of ABD?
Center will be different. No, center will also be same, no? It's literally the same circle, dude. Everything will be same. In
Okay.
the same circle, you will not be able to make two different triangles. Is it not possible to make multiple triangles?
Yes.
तो इनका सर्कल का सेंटर सेम होगा कि डिफरेंट होगा?
Same.
तो वही हो रहा है ABT और ABC का.
Yes, sir.
Obviously, the same circle is there, so R is the same. So if you do sine rule there, you can get BD is equal to 2R sine A by 2, which is same as ID, because we have proved it already. And now you can see that IA times ID, if you multiply IA and ID, you're getting R by sine A by 2 multiplied by 2R sine A by 2. The product is 2R smaller. That finishes the problem because now we just needed to find this. From here, we are getting OI square is equal to this. Is it clear what is happening?
Yeah.
So that is Euler's theorem, and this method is obviously much better than the trigonometry method because it has much fewer calculations. So you need to know this method of proof, but you also need to know the trigonometric proof because that is the more obvious proof.
Yes.
Okay. The next point is criteria for orthocenter. So this is the theorem. Let ABC be a triangle, be an acute angle triangle, and let D be the foot of the A altitude, be the foot of the A altitude. Let H be the point on the segment AD. Now we have to prove that H is the orthocenter of ABC if and only if dB into DC is equal to AD into HD. This is a very important result. We'll be using it in some questions also later. You need to understand what is happening here. So we are saying that there is a triangle like this, acute angle triangle, and H is a random point on the altitude, A altitude. This point is D. H is some point here. What we need to prove is that H will be orthocenter if this condition is true. This is a nice result because it tells us when points on this altitude are orthocenter, if AD, the length of the altitude times HD, is same as BD into DC. If that is happening, then that point H is the orthocenter. So if some distances are known to you, then this can be a handy result to figure out whether the point is orthocenter or not. So first we have to prove it. Try to do the proof.
Okay.
One side of the proof is pretty easy. If you assume that it is orthocenter, it is very easy to prove this. That is not the main thing that you have to try to do, because we have already discussed orthocenter, all the distances are known. If you already know it is orthocenter, it's very easy to prove. I hope everyone understands that it is easy to prove,
Yeah.
because we can find AH is 2R cos A, many things we can find, right? AD is C cos B, so HD also you can find. BD is C. BD would be AD is C sin B, and BD is C cos B, and CD is B cos C. So by simple trigonometry, you can prove whether those two sides are equal or not. You can check and do it. But the main idea is to try to prove the opposite. If this condition is true, you have to prove that H is orthocenter. Is everyone understanding that the direct side is very easy?
Yes, sir.
Once you assume orthocenter, direct proof should be doable, one side.
Yes.
Try to think of the other side. If AD into HD is equal to BD into DC, then H is orthocenter. One hint that I can give you is, before you prove this, you should either know or you should prove the result that if H is orthocenter of triangle ABC, then the reflection of H over the base BC lies on the circumcircle. Has anybody seen this before?
Yes, sir.
Yes, sir.
So first prove this. That should be a straightforward proof. This line is 90 degree. We can prove the triangles to be congruent.
Yes.
If H is orthocenter, We can prove congruency here, I think, because 90 common side, and I can show that this angle and this angle are same.
And sir,
In-
we know that A is reflection means HD is equals to DA also.
First, you have to prove this result. Do you know how to prove this?
No, sir.
So let's suppose H is orthocentered, then reflection of H
Yes,
lies
sir.
on circumcircle. So what I will do
Yes.
is not assume that it is reflection. I will just extend this line to meet the circumcircle at A dash.
Hmm.
Now in
Now,
triangle
sir, now
BHD,
we know that angle CBH is equals to angle CAD.
in these two triangles, we can say that this angle is equal to this, right?
Yes, sir.
Because of circle properties, this angle is equal to this. So this
Hmm.
angle is clearly going to be 90 minus C.
Yes, sir.
And we can say that if what is this angle? We can try to figure that out. So
Yes, sir. Sir,
that that
sir,
is going to be also 90 minus C, because this
yes,
is
sir.
a line joining B to the orthocenter, so it can be extended here and made a 90 degree here. So this is also 90 minus C. So obviously, because this was 90, this was 90, the triangles are similar and there is a common side.
HD is equals to DA dash.
So then that means these two triangles are congruent. And if these two triangles are congruent, then HD is equal to A dash D. Which means that if this point was orthocenter, its reflection is the A dash.
Hmm.
Reflection over the side BC is the A dash. Is everyone understanding this point?
Yes, sir.
Yes.
Now, sir,
Once you know this, it is over.
now it's proved, sir. The theorem,
How is it done now?
sir, because sir, due power similarity, we get BD into DC is equals to AD into DA dash, and since we know that A dash is reflection of H on BC, so we can unreflect it, means we can reflect it again on BC on the other side, and it will
Wait,
overlap the H point.
what have you said? Similarity? What are you saying?
ये सर मतलब पावर ऑफ अ पॉइंट जो सिमिलैरिटी से प्रूव होता है, तो हम उसे ये कह सकते हैं कि बी डी इंटू डी सी इज इक्वल्स टू ए डी इंटू डी ए.
AD into?
डी ए.
What is AD into DA? Why are you repeating the same thing?
ए डैश डी इंटू डी ए, सॉरी सर, ए डैश डी इंटू डी ए. एंड सर
We
वी
are
नो
saying
दैट.
power of point D with respect to circumcircle. Because of power of a point, I know that
बी डी
BD
इंटू डी
into DC.
इज ए डैश डी इंटू डी ए.
This is true, and we
ए
know
डैश डी
that
इज
A
इक्वल्स
dash
टू
D
एच
is equal to HD.
डी. यस सर.
But A dash D is equal to HD only if H is orthocenter.
So we can prove that also, just you did now, so it's done, sir.
So what we are saying is that it will become HD into DA is equal to BD into DC if H is the orthocenter, right? Because this is happening only when H is orthocenter. Correct?
Yes, sir.
So it is originally, this is the result from power of a point, but it will become this result when H is orthocenter, and therefore this condition is proved now. Is it clear what is happening?
Yes, sir.
Yes.
So basically now in any triangle, if there is a point on the altitude and you want to check whether it's an orthocenter or not, you should remember this result. always for orthocenter, this result is true. AD into HD is equal to BD into DC. So that is a good criteria to check for orthocenters. Okay, fine. So we have discussed three things so far: power of a point, Euler's theorem, criteria for orthocenter. The next one is known as Haruki's lemma. And it goes like this: given any two non-intersecting chords AB and CD, chords AB and CD in a circle and a variable point P, on the arc AB. Let E and F be the intersections of chords PC and AB. So PC and AB are intersecting at E, and PD and AB. PD and AB are intersecting at F. Prove that the value of AE into BF divided by EF doesn't change even if point P's position changes. Basically, we have to prove that the value of this ratio is constant regardless of the position of P. So first try to draw the figure to understand what is going on here.
Sir, arc AB which containing C and D or not containing?
Not containing CMB.
Okay, sir.
RKB is not. Two non-intersecting chords of a circle, variable point on the arc AB. Let's say this point on the arc AB. Let E and F be intersection of chords PC. PC chord intersects with AB at E, and PD chord intersects with AB at F. These are my two intersections. We have to prove that AE times BF by EF, the ratio is fixed, does not depend on the position of P. So P could be anywhere on this R. Is everyone understanding the question?
Yes, sir.
Okay. Here we'll join D and E and we will construct the circumcircle of PED. I have joined E to D and I have made a circumcircle for PED. Now, basically, the proof here will rely on the fact that the angle, if you see angle CPD, angle CPD actually does not depend on position of P, right?
Yes, sir.
Because it depends on the length of the chord CD.
Uh, Angles in same segment are equal.
So no matter where it would have been, I could have said CPD angle is same, right?
Yes.
So now what I will do is I will extend this chord. I will use that fact soon. So first we'll do is we have constructed this circle. We'll extend the line AB and it meets the circle at G, let's say. We can say that angle EGD, angle EGD is the same as angle EPD
Yes.
because it depends on this DE, right? And the
Yes.
DE chord remains fixed.
Hmm. Sir, but if we will rotate P, then the D chord will not remain fixed, right?
DE chord will still remain fixed because this angle is fixed.
Okay. Yes. Hmm.
Even if you rotate, no, because this angle is having same size, the length of DE will still be same only. You can
Yes, sir.
try and construct a different figure, but you have to maintain this angle, right?
Got it.
The figure will look different, but the length of this length is same because this angle is same.
Hmm.
And now because DE chord is same, we can say EGD will be equal to EPD, right?
Yes, sir.
Even if P varies on arc AB, correct?
Yes.
Now, for all positions of P, because we have now fixed this angle EGD, so that means that point G remains fixed on the line AB. The EGD angle is fixed. So the point G will remain fixed on the line AB. By that, what I mean is the extra length BG is fixed. How much extra you have to draw AB to get to G, that is fixed.
Yes.
So if this BG length is remaining constant, now we can do power of a point. BG length is constant. So notice what is happening because of this CPD being fixed. you know that chord DE is fixed. And because chord DE is fixed, we know that these two angles are there. So these two angles ensure that even if P varies, the point, this angle is same. And that means point G is fixed on the line AB, which means the length BG is fixed, even if the orientation of it will change if the point is slightly different. Right?
Yes, sir. The whole system will move.
The system will move, the chords are fixed, but the circle will be slightly different and all, right?
Yes, sir.
But BG length is fixed. Now we can do power of a point of point F and say that AF into FP is equal to PF into FD for the first circle. And we can also do for the second circle power of a point F. We can say EF into FG is equal to PF into FD, right? This is for first circle. This is for second circle. Do you understand what I'm writing?
Yes.
Is it clear what we have written here?
Yes.
So now we are getting AF into FB is equal to this, is equal to EF into FG. And now we can say that from here AF into FB by EF is equal to FG.
Answer
Right?
FG. Yes, sir.
And we know, okay, that is not done yet. I think we have to do a little bit more. So we can write, okay, I'll do it on the next screen. What we have is AF into FB is equal to EF into FG. And actually, it would be better if I do in the previous second. Here only we'll do. AF is actually AE plus EF into FB is equal to EF, and FG is actually FB plus BG, right? So what we are getting is EF and FB product will get cancelled, and we'll end up with AE into FB is equal to EF into BG. And now we are getting that AE into FB by EF is equal to BG. And the BG distance remains fixed. Therefore, we are getting AE into FB by EF is fixed. AE into FB by EF is fixed, regardless of where point P is chosen on the RKB. Are you understanding what I have done so far?
Yes, sir.
Yes, yes, sir.
Now, the reason we are doing this is because I want you to be able to use this. First of all, understand the pattern. The question did not have the second circle. So we can sort of remove the second circle when you're just trying to understand the basic theorem. The theorem is this, right? So the theorem was two non-intersecting chords and P is on one arc AB. The theorem is saying that from P you can join the other two chords and at points E and F it's intersecting the AB line, right? Now the
Yes.
theorem is saying no matter where you pick your P on this arc, always the ratios, this is my E dash and F dash. AE dash into BF dash by E dash F dash will be same as what we got here, AE into BF by EF. Do you understand what I'm saying?
Yes.
Yes, sir.
So this length multiplied by this length divided by this length is fixed, regardless of the position of the point P. Now, the idea is you should know the theorem, and from there you should apply it in a particular situation. So this is the homework. You have to use the theorem to prove butterfly's theorem.
Sure.
So basically this is point number 5 for us. You have to use point number 4, which is Haruki's lemma. I will state butterfly's theorem or butterfly theorem. It says let M be the midpoint of chord PQ of a given circle through which two other chords AB and CD are drawn. AD cuts PQ at X and BC cuts PQ at Y. You have to prove that M is also midpoint of XY. So the diagram of this is useful, and then you can understand why it is called butterfly's theorem. So there is a chord PQ, and M is the midpoint of the chord, and through M you are drawing two chords. One chord is called AB and one chord is called CD. This is my point M. This is the midpoint. Now AD cuts PQ at X and CB cuts PQ at Y. You can see that it looks a little bit like a butterfly's wings along. You have to prove that M is also midpoint of XY. Not just M was midpoint of PQ, right?
Got it, sir.
M was midpoint of PQ, and now we have drawn through M two chords and joined these lines. Now you have to prove that M is also midpoint of XY.
Yes.
The best proof of this will be using Haruki's lemma, which you have to do yourself.
Yes.
So try it out. This you should finish by the next class. Next class will probably be on Saturday. Also, like